density is mass or volume. So if we're given density and volume, we can solve for mass. By algebraic rearranging it, we can say mass, okay, is equal to, where am I at? Density times volume. Just rearranging the equation. If I'm looking for volume, I can say volume is equal to massity divided by density. Mass divided by density.
By density. Perfect.
So no matter what you're given, you can solve for it. So say you got a forensic case, they found a bullet, and you want to find the density of the bullet. So you got this bullet that they found at the crime scene. Okay, you weigh it, and it comes out to 6.38 grams.
Okay.
Okay, and then you want to, and we have a graduated cylinder. Graduated cylinder is a measuring tube that you can pour water in to measure the volume of the water. Okay, so say we put this exactly at 40.00 milliliters.
Okay.
The water is filled up to this point. And this is all water, right? So we take the bullet and drop it in the water. Okay, then the water's going to rise, right? Because we added a certain volume to it. And say it goes to 42.50 milliliters. It comes up to it. Okay, now we can solve for the density. We have a mass, we have a volume. Okay. So density is equal to the mass, which we weighed at 6.38 grams. The volume is going to be the difference between the 40 and the 42.5. How much the water level rose when we put it in. So the volume is 2.500 milliliters.
Okay.
So our density comes out to 6.38 divided by 2.5 comes out to 2.552. But we're good to only three single digits, which is our lowest number. So 2.55 grams per milliliter. And that's how you do density.
Perfect.
Okay. And that pretty much covers what we did on Tuesday.
Okay.
So we'll start with some new stuff here.
All right.
We'll give you a little chemistry to go along with the math here too. Okay. In chemistry, each element, if you look at the periodic table, this is your periodic table. A lot of information on the periodic table. This represents your different elements. That's cobalt, that's chromium, that's beryllium, hydrogen, etc. Okay. Every element is determined by the number of protons.
Okay.
Every atom has protons and neutrons in the center and electrons spinning around it. Okay. So you have protons, all has a positive charge, and neutrons, which are neutral, and electrons, which are negative, spinning around them. Okay. So the number of protons determines your element. Okay. So if you look at cobalt, you see that number 27 above it? It has 27 protons.
Okay.
So gold, Au. Okay. Au is right there.
All right.
Has 79 protons. So every element is determined by this number of protons. So, and protons have a mass of 1, neutrons have a mass of 1, electrons have basic mass of 0. They're very, very light compared to relative comparison. Right?
Okay.
So, but if you notice the number below it, like here where you have zirconium, you have 91.22, magnesium 24.31, phosphorus 30.97. That number is not a whole number. It's an average weighted mass. Okay.
Okay.
We have to do the math to calculate that because we have things called isotopes. Isotopes are elements that have the same number of protons, different number of neutrons. So they're the exact same element, okay, but they have a different mass. And they're found in nature at different percentages. So depending on which percentage of the ones you have, depends on the average atomic mass of these numbers. And we use these numbers in calculations from molecular weights and all kinds of things. And that's how we figure it out. So if we had, let's go down to right? Say we had an element, let's say Harley Davidsonium, right? That's our element. And then this element has 3 isotopes. You can tell I ride motorcycles.
Yeah.
Okay, 3 isotopes. We have a Harley Davidson. Let's see. So that's what I'm trying to free my mass and then Harley Davidson 131, Harley Davidson 132, and Harley Davidsonium 133. Okay, that's the
Okay.
mass number. That's the total numbers of protons plus neutrons.
Okay.
That's what's called a mass number. Okay.
Okay.
So let's say Harley Davidson 133 weighs 131.001, what's called AMUs, which are atomic mass units, which are just the small
Okay.
units, the protons and neutrons. And 132 weighs 132.371. And 133 weighs 133.121. Right? So those are the mass of the different isotopes.
Okay.
Let's say we have a percentage in nature. Say we have 73.00% HD131.
Okay.
We have 25. I can't do 25. I could. I don't want to go that high. That's a percentage. And say 132 is 15%.
Okay.
What's the average atomic mass for Harley Davidsonium, which we could hit? It's a typical problem you'd have to solve.
Okay.
So first of all, you got to figure the percentage of Harley Davidson 133. You know, the total percent has to equal what?
100%.
Has to equal 100. So, you know, this one has to be, what are we, 82?
Be 12%.
12.00%. Okay. So when you use the percentage, you just the value multiplied by 100. So we're going to use the
Okay.
value to calculate it. We just divide by 100. So we have 0.73%. We have 73. So 0.7300. That's a percent. That's the fractional value of Harley Davidson 131.
Okay.
And that weighs 131.001. Okay. That's the relative weight of that isotope.
Okay.
Okay. Then we got the other one is at 132. We have where am I at? That was like a 6. That's a 0. Okay. We have
All right.
0.1500 of the weight of that is 132.371. That's the fraction weight of that. The other percentage is 12%, so it's 0.12 times 133.12. That will give you the mass of each one according to the percentage found in nature.
Okay.
Okay, so 0.73 times 131.001 comes out to 95.63, 47 digits. And 0.15 times 132.371 out to 4.856. And 0.12 times 133.121 comes out to 15.97. Okay. If we add all those together, we'll get the average atomic mass of this compound, of this element.
Okay.
Because you know, each one of those sections weighs that much by their percentage. So you take 95.6, it's easier to calculate. 95.6, whoa, 95.63. And we add that to 4.856. And, oh, shoot, 4.856. And 15.97. And those add up to 116. And we're good to 2 places past the decimal.
All right.
0.46. So the atomic average mass is 116.46. So that's how we use math to calculate the average atomic mass of an element.
Perfect.
Okay, let's do. Let's do one that's on the periodic table so we can double check it too here. Let's say
Okay, perfect.
silicon. Okay, silicon has 3 isotopes, just like Harley-Davidson did. Okay, so silicon.
Okay, perfect.
Right? Silicon has 28, 29, and 30.
Okay.
28, 29, and 30. Okay. The mass of silicon 28 is 27.9769. Okay. The mass of silicon 29 is 28.97. .65. That's a 7. Okay. And silicon 30, 29.97. 9738. And the percentage abundances. Okay. It is 92.2297. That's a percentage. The other one is 4.6832%. And the other one is 3.0872. 3.0872. And those are all percentages. All right. So now you've got the mass of each one. And you got the percentage and nature of the dust. So you take the fractional amount of each isotope, multiply by the mass, and then add those together. So you'd have 0.922297 times its mass, which is 27.9769.
Okay.
Okay, and then you would have 4.6832. So you move the decimal points to 2 places. You have 0.046832. And that mass is 28.9. 28.9765. The other one is 3%, 0.03. 0872 times the mass of the isotope, 29.9738. So you calculate each of those, they'll tell you what the mass is, and then you add it together. So we should end up with silicon. Silicon has a mass of, the periodic table, it's around 28.09, something in that area.
Okay.
So let's do the math. We should get an answer here. 0.9222 97 times 27.9769 equals 25.803. And how many digits do we have? 1, 2, 3, 4. We have 6 digits. That's 5. We have 8030.
All right.
Next one is 0.04. Okay, 6832 times 28.97 65. And that comes out to, and again, 1, 2, 3, 4, 5 significant digits for this one. 1.3570. And the next one comes out to 0.030872 times 29.9738. Comes out to 0.925, and we get to find it, 0.92535.
Okay.
All right. So there's your values.
Cool.
The mass of each one. And so the isotope, the average atomic mass is the sum of those three numbers. So
Okay.
25.8030 plus 1.3570 plus 0.92535. And that comes out to 28.08. I'm good to 4 places past the decimal. 28.0854.
All right. So we're right in that ballpark.
Yeah, so it should have been silicone. Silicone should have been 28.09. And we ended up with 28.085, which is
Perfect.
good enough. Yep.
Absolutely.
So that's your average atomic weighted atomic masses are. And we're going to use those numbers to do calculations with.
Okay.
All right. And that's sort of simple math for that one. All right, light energy. Light energy, you're going to deal with two equations that you're going to know. Energy is equal to, let me do the other one first. Makes a little more sense. Let's erase that. C is equal to lambda nu. C is the speed of light. Okay, speed of light is 3.00 times 10 to the 8 meters per second. That's the speed of light.
Pretty quick.
Yeah, it's really quick. Lambda is your wavelength.
Okay.
And mu is your frequency. Right? So if you've got a sine wave, okay, the wavelength is the distance from the peak or crest of one wave to the peak or top of the other wave.
Perfect.
That's your wavelength.
Okay.
Okay. It could be very long like that, or it could be very short like that. The shorter that wavelength, the higher the energy.
Okay.
There's a lot more classical capacity. The frequency is how many times it passes one particular point per second. Per second is hertz. So 60 hertz is 60 times per second. Okay. 120 hertz is 120 times per second.
Okay.
So you put a point on this line, and how many times a wavelength will pass that point is your frequency.
Perfect.
Okay, so that's your first formula. C equals lambda mu.
Okay.
Second formula we're going to be is energy equals h mu.
Okay.
Where where the mu is your frequency still, and h is Planck's
Constant.
Planck's constant.
Okay.
Yeah, the Planck's constant is 6.634 times 10 to the minus 34 joule seconds. That's a J. Okay, so those are constants. Speed of light and h are constants. They stay the same.
Okay.
Okay. So now you can solve any equation you want for frequency or for wavelength if you're given the energy. So if we calculate energy, if you're given frequency, you plug frequency in.
Okay.
If you're given lambda, what do? You got to substitute your equation, right? Okay, so
Correct.
C equals frequency. C equals frequency times lambda. So frequency is equal to C divided by lambda.
Perfect.
Okay, so instead of writing H equals H nu, you can write E equals H, and instead of frequency, we can write C over lambda. Okay, so if you're given the frequency, you can solve for the energy. If you're given the
Okay.
wavelength, you can solve for the energy. Okay, so whatever we need to do, we can solve for it. I'll do a couple examples there.
Okay.
We do that, we do that. Okay, so a beam of red light. Okay, red light's in the visible spectrum, has a wavelength of 720 nanometers.
Okay.
I'm having a hard time writing this. 720 nanometers. Okay, that's a wavelength.
Okay.
You want to know what the frequency is. Okay, so you're looking for frequency. You have the formula C equals wavelength times frequency. So we're looking for frequency. Frequency is C divided by lambda.
Okay.
C is 3.00, like you said, really fast, times 10 to the 8 meters per second.
Okay.
Okay. And the wavelength is 720 nanometers.
Okay.
Now, when you look at that, you realize meters are on the top, nanometers on the bottom. Those don't match.
Correct.
You have to have apples to apples, oranges to oranges, right? So
Correct.
let's put nanometers on the top. So
Okay.
it cancels here, and then we'll put meters on the bottom and
Okay.
make this equal to 1. Nano means what in the metric system?
That would be 10,000.
No more, 10 to the minus 9.
Oh, that's yeah, that's
So
much smaller.
1
Than,
billion.
much smaller than I was thinking.
Yeah, nanometer is really, really small. It's 10 to
Yeah,
the
very
minus 9
small.
meters. Because you got millimeters, which is minus 3. You got micrometers, which is 10 to the minus 6. Nanometers is 10 to the minus 9.
Okay.
And that's really quick.
Very quick. Yes.
So nanometers cancel.
Okay.
Meters cancel. And you're left with what? You're left with per second. And per second is hertz, which is your frequency.
Yeah.
This is what you want.
Exactly.
So we take 3. So doing the math part, we would do 3 divided by 720. And that comes out to 0.004166 Okay, and then we got 10 to the 8th. And we bring the 10 to the minus 9 out, it has 10 to the 9th. So that becomes 10 to the 17
Okay.
per second. So then we put in scientific notation, and we're only good to 3 significant digits. That's our measured wavelength.
Okay.
So we're good to write there. So we have 4.17, make that between 1 and 10.
Okay.
It's 10 to the what? It was 10 to 17. We moved this to 1, 2, 3 places. We made it bigger. So you have to make this smaller by 3 places.
So 10 to the 14th.
10 to the 14th hertz or per second. It can be written, either any of those ways can be written like that.
Perfect.
Okay? And that gives you your frequency. That gives you your frequency.
Nice.
All right. And let's see what. Let's do a couple energy ones here too.
Okay.
Okay, so one of the questions in the book here says, the energy in joules of a beam of light whose frequency, so you want energy.
Okay.
And you want this a beam of light whose frequency, okay, is equal to 6.98 times 10 to the 14 hertz. So let's calculate. Remember, one of the formulas is energy equals H mu.
Okay.
So we're already in frequency with that. So plug our numbers in. H is Planck's constant, 3.3, 6 point, what is that? 6 point, yeah, don't want to blame Planck's constant on that. 6. Really? I lost my equation too.
Oh, no.
Oh no. All right, we can put it back. Energy equals H mu. Frequency is equal to 6.98 times 10 to the 14 hertz.
Okay.
All right. So energy, Planck's constant, 6.626 times 10 to the minus 34 joule seconds.
Okay.
And our frequency is 6.98 times 10 to the 14 hertz, which is per second. So the per seconds cancel. There's per second and that's seconds, and you end up with joules. So our energy would equal 6.626 6.626 times 6.98, and that equals 46.24948. And we're good to 3 significant digits. We measure that out. So it's going to be 46.2 times 10 to the, we got 10 to the minus 34 and 10 to the 14. Minus 34, make sure, yeah. Okay. So 10 to the minus 34 and positive 14, down to 10 to the minus
20.
20, right?
Yeah.
Got it. 10 to the minus 20 joules. And sign to notation, you would put 4.62 times 10 to the negative, and we make this number smaller, make this one bigger,
All right.
10 to the minus 19 joules.
Cool.
Makes it, math make sense?
Absolutely.
All right. Let's try one that does the all right. It says, what is the wavelength of a photon? Photon is a unit of energy given off by electrons. Okay. In other words, a little more chemistry here. You have the
Okay.
nucleus. The nucleus is the center, right? Your protons and neutrons.
Correct.
And these electrons fly around it. These electrons are in little rings. Okay. So these electrons go around in different, what's called orbitals. We're going to do that in regular chemistry. But when you apply energy, like a spark or something like that, these electrons get excited and they move to different energy levels. They move up. Okay. You can put in a laser light, you can put in kind of light energy, you can put in a match for heat energy, and it moves the electron further at the nucleus. Okay. Once that energy is gone, that electron is out further away now, right? It slams back down. So it comes back down to its original ground state. When it comes back down, a photon of energy is released. Okay? And it releases a different color. That's how fireworks work. Okay. All the different elements are going to have different colors because all the different colors, when those photons are excited by the spark of the firework, they all slam back down and give off that different color array in firework display. So those are photons of energy you're seeing.
Okay.
So let's clear this and we'll go there. So a photon, it says, what is the wavelength of a photon with an energy of 3.75? So you're looking for a wavelength. Okay. And you're given with an energy of 3.75. 3.75 times 10 to the minus 19 joules. All right, So, you know, this is good. This is its energy. Right. So energy
Okay.
equals H mu. But we're looking for wavelength, right? So
Correct.
we also know C equals lambda mu, wavelength times frequency. So instead of writing frequency, okay, I can write C over lambda. So energy equals H, and then instead of frequency, I put C over lambda. Okay. And I'm looking for lambda. So lambda, rearrange this equation here. Lambda equals HC over the energy. We know the energy, we know H, and we know C. So now we can calculate the frequency.
Cool.
And all I did was rearrange my equations and then I substituted these in. These are my two equations that I know about light energy. And I use those to substitute in to get lambda and energy together. And then I rearranged it to solve for the wavelength. Does that make sense?
Absolutely.
All right, perfect. So H is Planck's constant, 6.626 times 10 to the minus 34
Okay.
joule seconds. Speed of light, 3.00 times 10 to the 8 meters per second. And the energy we have was 3.75 times 10 to the minus 19 joules. Now, and joules cancel, seconds cancel, and we're left with meters. So let's do the math. You have got 6.626 times 3 divided by 3.75 equals 5.3008. You're good to 3 significant digits, our measured value there. So
Okay.
5.30, and it's going to be times 10 to the, we got 10 to the minus 34. We got 10 to the 8. And we got 10 to the 19.
All righty. So 10 to the minus 7.
So 10 to the minus 7 meters. Yep, okay.
All right.
Now, to compare that with frequencies of light, visible lights, things like that, we have to convert that into nanometers.
Okay.
And so nanometers, we usually do a conversion into, again, nanometers, nanos 10 to the minus 9. That comes out to, and then we get 10 to the minus 2. Comes out to 530 nanometers. And we look at that on the visible spectrum. And is that red light? You have a 530, it's green, like a dark green light. So the
Cool.
color of light given off here with that kind of energy would be green. All right, makes sense?
Makes sense.
All right. That's the math, that's the calculation for energy. Okay, those are the only two equations we have for that. Let's make sure you go over all the math parts for this. And I'll go over a little something with you here. Well, yeah.
Okay.
A lot of people have trouble with electron, valence electrons. And
Okay.
the electron configurations for different elements. And basically, we go to the periodic table. And we talked about the nucleus. We talked about these electrons that surround it. Okay. These electrons that fly around it don't really exist between it. They exist at those different ring energy levels,
Correct.
but they do not exist between energy levels. It's like they'll exist over here, then they'll exist over here. Okay, so electrons have special properties where they have a wave property. So they have no mass at certain times. So
Okay.
they'll exist at one energy level, then it'll never cross through it. Kind of interesting things like that. So we
Correct.
can't talk about where an electron is located. Say you have a microscope and you want to look at something. You shine a light on it and you see the image, right?
Correct.
Okay. If you shine a light on the electrons, they move.
Yeah.
So you can't know where they were. You can't look at them. You can't see them because they're gone now. So all we can talk about is probability of where an electron is going to be at any given point in time. And it's going to change. That's a lot with chemistry. Those electrons change a lot. They determine a lot of things with chemistry. Okay, but you can only determine a probability of it. So we got to give them an address of where they can occur, and we go through these different energy levels. So, like I said, this is kind of a little beyond, but you'll get this in chemistry also. Okay, so this is our periodic table. We're going to slide hydrogen into this spot right here.
Okay.
Okay, just for now. So these two groups, two columns, these are what's called s orbitals. These 6, okay, are what we call p orbitals.
Okay.
These 10 are what we call d orbitals.
Okay.
And these 14 are what we call f orbitals. So you got
Okay.
S, P, D, and F.
Okay.
S's always start with 1. P's always start with 2. D's always start with 3. And I'll bet you can guess what F start with.
Let's go 4.
Let's go 4. So if you want to give an address, you're just going to count for each filled unit. Everything
Okay.
filled with 2 electrons. So we start with, we look at hydrogen. Hydrogen is going to be 1s1. It means it's the
Okay.
first energy level. It means it's in the s orbital and there's 1 electron.
Okay.
Helium. Helium is going to be 1s2
Okay.
because there's 2 electrons now. And now that completes this whole row. Then we drop
All right.
down to the second energy level. It's a continuous one, so you don't just go by itself. So we already filled the first one. So we have 1s2, 2s1.
Okay.
Then beryllium would be 2s2.
All right.
Then we're going to go, so we keep going across. And now we're at the P's. Remember, the first P starts with a 2, right?
Correct.
So if you want to go to carbon, it would be 2p2. Nitrogen would be 1s2, 2s2, 2p3.
Okay.
Is that making sense? Is it just go order by order?
That absolutely makes sense.
All right, perfect. Now the tricky part gets to where you get to argon here. Okay.
Okay.
And then you drop down and you get to the D's. Remember, the D's start with 3.
Okay.
Okay, so let's go back to the periodic table here. I have it drawn all over. Ah. There you go. All right, so let's do iron.
Okay.
Okay, so let's start with the top. You have 1s2. That fills that first row.
Okay.
Then you have 2s2, 2p6.
Okay.
That fills the whole second row. Third row, 3s2, 3p6. And it gets us right to here, right?
Correct.
Then you drop down to 4s2. Now remember, D start with 3. So even though it's in the 4th energy level, this is 3d, 1, 2, 3, 4, 5, 6. And then it continues on to 4p going across. That's the big
Okay.
trick, because you got to remember D start with 3. And again, this is like an address of where the probability of finding an electron is. Okay. And when we do Lewis structures, we'll draw a figure of the, we want everything to have 8 what's called valence electrons. Valence
Okay.
electrons are electrons in your outer shell. Okay.
Okay.
Once it has 8, it fills it up. These are called noble gases. This column right here. And these are all S2, P6, which gives you a total of 8. It fills your valence electrons with 8. They're very stable. So they're called noble gases because they don't react with any other elements, even themselves. They're too snooty. That's why they're called noble.
Okay.
Okay. So those, they have valence electrons equal to 8. Everything else is going to want to fill that valence shell. And we'll show you how we do that when we calculate each one of those. All right.
Okay.
All right. So that deals with our electrons. Okay. And when you get to the bigger ones, like say you want to go like strontium, that's a lot of writing.
Yeah.
So we have abbreviations. Chemists are usually lazy people. Okay. So we go back to the nearest noble gas. So we go backwards to the nearest noble gas. The nearest noble gas going backwards is krypton.
Okay.
Okay. So we put krypton in parentheses. And then we go 5 is our energy level,
Okay.
5s2. And that's strontium. Then we don't have to write out 1s2, 2s2, 2p6, 3s2, and all across it. So we just back up to the nearest noble gas because that's stable. That's
Okay.
our core.
Okay.
Because there's no, once those valence electrons are filled, that core is filled. All right. So you back that to a core, and then we can use that as our abbreviation, which is a lot less writing.
Yeah. Yeah. That definitely eliminates a lot.
All right. Let's go into the next chapter here and let's go through the math here. So we're going to do some Lewis structures and the octet we just talked about.
Okay.
So when we're talking about valence electrons, all chemical reactions depend upon the electrons on the outer ring.
Okay.
These are called valence electrons, all reactions. Okay, all chemical reactions. Nuclear reactions are a whole different ballgame.
Yeah.
We'll do that. I think chapter 16, the last chapter you're going to get is nuclear reactions.
Okay.
We don't do those in the chemistry lab.
Okay. Yeah. Yeah.
So we're dealing with electrons, the outer shell. That's what causes your reaction. So,
Okay.
and everything wants to have 8 except hydrogen. Hydrogen wants to have 2 because it fills it. Because once this is filled, we're good. So hydrogen wants to have 2. It's called the duet rule. Everything else is octet rule.
Okay.
All the ones in this first column where it says 1A, they have 1 valence electron.
Okay.
2A has 2 valence electrons.
Okay.
3A has 3 valence electrons. 4A has 4 valence electrons. Guess what 5A has?
I would imagine 5.
5, 6, 7, and 8A has 8 valence electrons, which is what you want to make it stable. So that becomes stable. So all these are your noble gases. Everything wants to be like a noble gas.
All right.
They want to have 8 valence electrons. So just look at your periodic table, you can tell 1, 2, 3, 4, 5, 6, 7, 8, what valence electrons they have. Now, if you look at this middle section, I kind of skipped over from here to here. Okay, these are called transitional metals or transitional elements. Transitional elements means they can vary on the number of valence electrons that they have, depending on the oxidation state of the element.
Okay.
Okay, so manganese can have 4 or 2 or 1. Iron can have 2 or 3. Copper can have 1 or 2. It all depends on what and there's different ways that we're going to name those things by using that a mathematical way of naming those elements. Right? So that's how the periodic table is set up. So
Okay.
these valence electrons are we going to use in writing the structures. Okay. Now on the periodic table, before we go over this here, you see this line right here. We have purple ones to the left and green ones to the right.
Okay.
Everything to the left is a metal. Everything to the right is a non-metal. Okay?
Okay.
Everything on that line, those yellow colored ones, those are metalloids. They have properties of metal and a non-metal.
Okay.
So when we bind these electrons together, when you can either have metals don't bind to metals. You either have a metal and a non-metal or 2 non-metals.
Okay.
If a metal and a non-metal combine, okay, that's an ionic bond. The electrons actually move from one to the other, and it forms a charge, that positive charge that pull it together. Covalent bonds, if it is a covalent bond is two nonmetals, and those share electrons.
Okay.
Okay, and that's really where Lewis structures. So that's our important points with that. And we'll be able to name them. Let's go with a couple little how to name these things so that we're talking about here. We'll do that. So when we name it, metals always come first in a name.
Okay.
Okay, so if we have, let me get this periodic table up here. So if we have sodium and we have chlorine, okay, that comes together. Na, you can see right here, has one valence electron.
Okay.
Chlorine has how many?
7.
7. Everything wants to have 8, right?
Correct.
So sodium donates this electron to chlorine. Okay, now chlorine has 8 valence electrons. So you get Cl and a minus charge because you have one extra electron.
Okay.
Because your charge is determined by the relationship between your positive charge and negative charges. So chlorine has 17 protons. It has 17 electrons. Now it has 18. So it's just like argon, which is stable. So Na becomes plus because it lost an electron.
Okay.
It's got 8 electrons back here because it goes back to its noble gas configuration. It has 10. So this plus and minus charge attract, and that's what bonds it together.
Perfect.
Sodium chloride is table salt.
Yeah.
Okay, it bonds together. So when you name it, you name the metal gets the name on the periodic table. So
Okay.
you call it sodium. And then the chlorine, you change the ending to IDE.
Okay.
So the second name came to an IDE. So that's why sodium chloride is table salt.
Okay.
That's sodium chlorine. Okay. And they're going to match the charges. Sodium is +1, chlorine is -1. It's 1 to 1. You have to balance your charges. So when Na and Cl combine, it has to be a neutral compound. Okay. So the formula is NaCl. So let's take calcium. Okay, there's calcium. Okay. Calcium is going to have how many valence electrons?
If I can see it, I have my glasses on too.
Oh, it'd be
Oh,
two,
there we go.
right?
It has 2. Yeah.
So calcium has 2 electrons. And let's go oxygen. Oxygen has 6. So electron's going to go there, electron's going to go there. Okay. So calcium and oxygen combine. Okay. Calcium gives off 2 electrons. Oxygen accepts 2 electrons. Okay.
All right.
So it's going to be Ca and then 2 plus and O 2 minus. Because it lost electrons, gained 2 electrons. So the formula would be CaO. So it'll be calcium oxide.
Nice.
Let's do calcium and chlorine. Okay. So calcium, we said is going to have a +2 charge, right?
Correct.
Chlorine is going to have a -1 charge. Okay. Now, when they combine, they have to total 0. Okay. So we have 1 calcium. How many chlorines do you need to combine with it to make it total 0?
2.
2, right? So CaCl2. That's a subscript. The subscript tells you how many elements have to combine. When we're dealing with the charges like this first column is +1. This column is +2. This column is +3. Okay?
Okay.
So yeah, +1, +2, +3. Those are your valence electrons. Now, removing the nonmetals. This column here with carbon. This carbon here is neutral. Okay? There's no charge on carbon. That's what's used in organic chemistry. It can bond to a lot of things. Has a lot of cool properties with it. Okay?
Okay.
So then the next one, let's go to, this is -3, -2, -1. So you got 1, 2, 3, neutral, -3, -2, -1 for the charges. Because
Okay.
like nitrogen is -3 because it has 5 valence electrons. It wants 3 more to have 8. So it's -3 charge. Sulfur.
Okay.
Sulfur has 6 electrons. It wants 2. So it's a -2 charge. Okay. So give me kind of a little bit of chemistry here with the math part of everything.
All right.
You'll get into this. So you're going to name it calcium chloride. Okay. You don't ever name this subscript in an ionic compound.
Okay.
You will in covalent, because you don't know how about it. But ionic compound, you never name that subscript,
Okay.
right? So that's how they combine. And like our computer chips are silicon, right? What's the biggest problem with if you take a computer and you speed it up, you tack out, you increase acceleration. What does your chip do?
I'm sorry.
On a computer, we use silicon, right?
Correct.
Okay. When we step them up, we speed them up, those
Uh-huh.
chips tend to overheat,
Oh,
right?
Correct. Correct.
That's the problem we have. Now, remember in the periodic table, those columns are all going to act the same. So what the military is doing is instead of using silicone, they're using carbon in their computer
Oh
chips.
wow.
Carbon is diamond.
Yeah.
It's the hardest substance we have on Earth. I don't care how fast you clock that chip, you're not going to find it. So these supercomputers that the military is using, they can have speeds unbelievable.
Oh my God.
Because they can't melt. There's no fans needed.
Yeah.
And these things can fly with calculation. That's because in the periodic table, it's going to have the same 4 valence electrons for bonding in a computer chip and allow it to process for computer processor, which is really cool.
That is really cool.
Yeah. So you're getting everything. So let's look at our periodic table and let's name a couple of these. Okay, so that's how to do ionic compounds.
Okay.
Covalent compounds. Say we have NO. Okay. Now, when there's no numbers here, we assume it's a 1, right?
Okay.
1 nitrogen, 1 oxygen. We don't put 1 if it's a 1.
Yeah.
So this would be named nitrogen. And this would be mono
Mm-hmm.
oxide.
Okay.
There's 1 oxygen. Okay. We only call it mono for the second one. We don't use mono for the first one. We don't
Okay.
say, like if we had CO2. CO2, we don't say mono carbon dioxide.
Correct.
We say carbon dioxide. So we only use a mono nomenclature if it's the second one and there's only one.
Okay.
Okay? But if it's a covalent compound, which means they're 2 nonmetals, we have to name the subscripts because there's no charges. We don't know what the charges are. They're all negative. So there's no balancing charge. We have carbon dioxide.
Okay.
So let's pull up. Well, that one's even worse than the other one. All right. So let's, if I was going to combine sodium and oxygen, what would the formula be?
Let's see where we have sodium. Oh, that'd be NaO2.
Other way around.
Oh, hold on. Let me-
Sodium is +1, oxygen
Oh,
is
okay.
-2, right?
Oh, okay. Okay. There's sodium. Oh,
Right.
there it is right there. Okay. So we're going to be Na2. Oh,
Right, perfect. There's a real easy trick. It's called the crisscross rule.
okay.
They might tell you, but they might not. Just take this number, put it here. Take that number, put it there.
Oh.
22,
There you go.
right? Let's do strontium, which is SR, which is right here. And let's do phosphorus.
Okay.
So strontium is what charge? This column is
It's going to be a +2.
+2, and phosphorus is a
Phosphorus is a +3.
not plus,
Oh, -3.
minus. Perfect. 3 minus. So crisscross it. SR3 P2. Strontium phosphate. Right? And if SR is +2, 3 times, that's +6. Phosphorus -3, 2 times, that's -6. Okay?
All right.
The only thing with the crisscross rule is if you have higher numbers that can be reduced, you have to reduce them. Like if
Okay.
we had magnesium and oxygen, that's 2+ and 2-, right?
Mhm.
So you wouldn't put Mg2O2, you put
Correct.
MgO. You reduce the lowest common denominator possible.
Okay, perfect,
That'd be called magnesium oxide.
perfect.
All right, so those are covalent. So the difference between covalent and ionic is covalent, you name the subscripts, ionic, you don't. Okay? And the second
Yeah.
element is always IDE ending.
Okay,
Now, one more rule you're gonna have to find out.
okay,
Transitional metals. Transitional metals, you don't know what the charge is. So you got to figure it out
okay,
and you got to put it in there. If we had a compound like Fe, oh, okay. Yeah, we iron oxide,
okay,
but you don't know if it's iron, like diiron oxide, triiron oxide. You don't know how many there is of it.
okay.
You have to tell me the oxidation charge on it. So if oxygen is 2-, then iron has to be what to make it balance?
Has to be 2+.
2+. So you put in Roman numerals, you put iron 2 oxide.
Oh, okay,
So Fe2O3. That'd be iron, Roman numeral what? Then oxide. Now there's 3 oxygens, right?
hmm
Each oxygen is -2. That's -6.
correct.
So you have 2 irons. So each one has a charge of what?
Has to be +3.
Perfect. Iron 3 oxide. Most students mess that up. They're going to put iron 2 because there's 2 right here.
Ah, okay,
But it's the charge on that compound. Okay, and that's all there's to it. If you had,
yes,
yeah, if we put on cobalt, let's do. If I told you the formula was cobalt 2 fluoride, what would the formula be?
let me see if I can find.
It's cobalt.
Okay, it was cobalt. Oh, okay. So it's going, fluoride's gonna have it's gonna be a charge of 1-. So it's going to be COF2.
Perfect. Yeah. Perfect. So now you got so when you look up, if it's in this area,
Mhm.
it has to have and you have to know what charge it is. Now there's a couple exceptions to this. There's always exceptions. You
Yeah.
can't do it without exceptions, right?
Of course.
There's 3 exceptions: silver, zinc, and cadmium. Silver is always +1.
Okay,
Zinc and cadmium are always +2.
okay,
So that's your exceptions. Those don't change. Everything else can change in there. Okay? But that's how to name compounds, by using the numbers to manipulate them so they balance evenly.
okay.
Cool. So we got that. So, okay, so we talked about, let me just show you an example of sharing electrons.
Okay.
We talked about, so it's covalent. We talked about how to name them because they share electrons. So if we had, let's take water.
Okay,
H2O. So oxygen, 1, 2, 3, 4, 5, 6 valence electrons, right?
correct.
Hydrogen has 1. Hydrogen has 1. So when you have 2 electrons between 2 elements, that's a bond. So it's
Okay.
H bonded to O, bonded to H, with our other electrons there.
Perfect.
So a chemical bond, every time there's a chemical bond, there's 2 electrons in it being shared.
Okay,
These up here, these are called non-bonding electron pairs.
okay,
They always occur in pairs, and they're non-bonding, they're not in a bond.
okay,
And you use those in determining shapes of molecules and determining what they're gonna look like. Because shapes determine everything. Shapes determine how our drugs interact and everything else
Exactly.
in the body. So like pharmaceuticals, right? The shapes that
Correct.
actually bind to the receptors.
Correct.
Okay, so we'll be able to do that coming up in chemistry.
Cool.
So that's how they share. And when we name, we'll do one more thing with naming, then we'll call it even for tonight. So so if we have a double bond, you'd have 4 electrons. If you had triple bond, you'd have 6 electrons. Okay,
Okay.
2 in every bond, right?
Correct.
Okay. So that, and then I want to go over the naming. So when we're naming subscripts like P4O10,
Okay.
okay, mono is for 1. There's di, tri, tetra,
Okay.
2, 3, and 4. Penta, hexa, hepta, octa, nona, and deca. And that's
Okay.
That'll be in the book. You gotta memorize all that. But we use that in organic chemistry also. So this would be tetra, phosphorus, deca, oxide. So you name the subscripts.
Okay.
Okay, and you have you follow the chart, just name like that. If you had N2O5, that would be di, nitrogen, penta, oxide. Remember, the name for the first one is always just the periodic table. And we
Okay.
changed the last one to IDE.
Okay.
Right? And then we name the subscripts. If it's covalent, we have to name those subscripts because we don't know. If it's ionic, we know because it's balanced by charge.
Perfect.
So we don't have to name it.